All right, section 15.2, this is on gases. And here's the objectives. Be able to explain the relationship between molecular motion and temperature. Of course, we're talking about temperature in Kelvin. Describe random motion of gaseous molecules and how the collisions cause pressure. And also be able to explain how zero kinetic energy relates to 0K. All right, so first of all, with gases, one of the things about gases is that they can expand to fill that container no matter what size. So if you have something in a little small container and then you open that, it would expand to fill the bigger container, and it would do it pretty much instantaneous. And on the other hand, you can do the opposite. You can take gas and you can put pressure on it and you can compress that thing down to, fractions of the original size. And so that's what gases. They can expand, they can be compressed. If you compress things far enough and compress them to where the particles would be touching each other and they couldn't move away from each other, then it would actually be a liquid. So if you need to liquefy gas, you can, usually what we think of is you just cool it, but you can also compress it, or combination of those two things will turn them into a liquid. When you put gas molecules in a container, I've got these gas molecules in here, and they're moving around, they bounce against the sides of the container. And when they do that, they exert pressure on the side of the container. And remember, there's trillions and trillions of these molecules bouncing around, exerting pressure on this container. So if you think about, blowing up a balloon, the particles inside the balloon, they're moving all over, running into the sides of the balloon, and that's what forces the balloon out. That's what gives the balloon its shape, is the particles, these billions and billions of gas particles bouncing into the side. As far as temperature and kinetic energy, those two things are closely related here. If we're talking about kinetic energy, what we mean is energy of motion. So anything that's moving, if your car's moving, it's got some kinetic energy. And there's a formula for kinetic energy, 1/2 mv squared. And notice that if you were to double the mass of an object, you would double its kinetic energy. But if you double the velocity, because the velocity is squared, you would actually get 4 times the energy. So the speed or velocity of an object causes more change in energy than does just changing the mass of an object. And when we're talking about gases, we're not going to be changing the mass, we're going to be changing the velocity. The label for this, if you think of the label for kilogram, or for mass is kilogram, and the label for velocity is meters per second, and if you square it, it'd be meters squared, seconds squared. So that, the label for kinetic energy could be kilograms meters squared per second squared, but that's kind of a too big a one. So they just come up with what they call the joule, which is capital J, and that's our abbreviation. So these two things are equal if you wanted to convert them. So the joule is the SI unit for energy. So anytime that we're talking about energy, in this case we're talking about kinetic energy, we would use joules. This particular formula, I don't know that it's important for you to memorize and use on the test, but what they're saying is that the average kinetic energy of gas particles is equal to 3/2 r. R is a constant, and we're not going to worry about where that comes from for right now. The big thing that I really want you to understand is T. So we're saying that kinetic energy is equal to this constant, and all that 3/2 could be kind of thrown into that constant too. But it's really dependent on the temperature of the object. And the key to this is the temperature must be in Kelvin. This is probably one of the biggest things you got to remember in this chapter is you cannot use Celsius temperatures. You have to use Kelvin, because think about it, if this was Celsius, we would be saying, hey, if something were 0 degrees C, it would no longer have any energy, it couldn't be moving, which would mean then that air in your car tires on a freezing, day that it's below zero, there wouldn't be any pressure at all, and that's not true. It's based on Kelvin, so that'd be 273 Kelvin. So we still got a lot of temperature there. If we had air at 0 Kelvin, now we wouldn't have any movement. Now those gas particles will all just be laying down and not moving at all. So that's the big key. That's the big thing about this. So even though that kind of formula there, the big thing to remember is whenever we're talking about temperature, it must be in Kelvin. So if we get everything down to 0 K, what we're saying is that there's no movement. So that's how they define. That's why there's a bottom to temperature, because the bottom to temperature is when the particles quit moving. When the particles quit moving, that's 0 K. And that's the end of section 2.